Okay, morning everyone. Welcome back. So I'm filming another probability distribution video, and in this video, I'm going to talk about the gamma distribution again, but also the relationship between that and the exponential and the Erlang distributions, which are just special cases of the gamma distribution. So I'm filming this particular video in my office at work, and there's quite a lot of background noise, so hopefully that won't disturb this video too much, but I will persevere regardless. Okay, so in the previous video, I described how to simulate data that follows a gamma distribution and how to investigate the properties of that distribution using the PDF, the probability density function, and the cumulative distribution function, the CDF. The gamma distribution, you will hopefully remember, is a continuous distribution function. It's used to model the time, things such as the time between independent events that occur at a given rate. And the three main parameters for the gamma distribution are the threshold, also known as the loc, which is the starting value, the shape, and the scale. And these specify the starting value for the distribution, as I just said, that's the threshold, the number of events being modelled, that's the shape, and the rate at which events occur, respectively, and that's the scale. It's usually given as a rate. In this notebook and in this video, what I'll do is I'll develop our understanding of the gamma distribution a little bit by visualizing the gamma distribution to show how changing these parameters alters the appearance of the distribution. And I'll also discuss the relationship between the gamma and two other distributions, the exponential and the Erlang distributions. And those, as I said at the start, these latter two distributions are just special cases of the gamma distribution. Okay, so let's get started. I'm going to import some software libraries. I'm going to import numpy as np, pandas as pd, scipy.stats as stats, and we're doing some plotting, so I'm going to import matplotlib.pyplot as plt. Okay, so let's look first at a gamma. We'll generate some data that follows a gamma distribution, and we'll kind of adjust the threshold or loc parameter. So to do this, what I'm going to do is I'm going to create an array of data, and that's going to be 100 data points on a scale from -15 to 40. And this object that I'm going to create, this variable, this object x, it's going to basically be an array of 100 data points. And I'll use that to define three gamma distributions, that array, that vector of data points. And in this case, what I'll do is I'll set the shape and the scale parameters both equal to 3, and set the loc, the threshold parameter, to 3 different values. Okay, so, and those values are going to be -10, 0, and 10, and we'll look at how. So the loc basically shifts the distribution left and right. So I'm creating a new object called x using the numpy linspace between -15 and 40, 100 data points. And then I'm basically creating 3 objects, loc1, loc2, loc3, and they're basically, I'm using stats.gamma.pdf, so we're creating a probability density function that follows a gamma distribution. The data that we're inputting is this vector, this array, this numpy array called x. And as I said, I'm setting, for all 3, I'm setting alpha, which is the shape, to 3, and the scale to 3. And the thing that's different between the 3 is the first one's got a starting value, a threshold, a loc of -10. The second one is 0. The third one is 10. And then I'm going to just plot that using, plot all 3 on the same figure using matplotlib. And there, let's have a look at them. Okay, so what you can see here is this figure here highlights how changing the threshold for the gamma distribution adjusts the starting value and shifts the distribution left or right. So they're all roughly the same shape, but the value at which they start differs on the x-axis. So we can see that for the blue line, starts at -10, you start to already see some positive probabilities for values from -10 onwards, upwards along the x-axis. So it's the most left shifted of the 3. The orange distribution shows probability starting at 0. Yeah, you can see that there. And we can see the green line. You don't see, everything's got 0 probability until we reach 10, +10, which is the value we set for the loc. So all lower values than 10 for the green line that we've set there have a probability 0 and hence the flat line. So that green line there is clearly the most shifted distribution of the three. Okay, so that's what adjusting the threshold, the starting value does. It kind of moves it left and right. As you would expect, it intuitively makes sense, I think. Let's have a look at what adjusting the shape parameter does. Okay, so remember shape alpha, this is the number of events that we're modeling. Again, I'm going to plot three gamma distributions. I'll set the loc to 0 and the scale to 3. So the loc is 0 for all three. The scale is 3. We're doing a similar thing to what we did above, but I'm actually the actual vector of numbers. I'm just starting at 0 in this case because we're setting the loc to 0. We want the loc the same for all of them. Okay, and we're going to adjust the shape parameter alpha. And remember, that captures the number of events we're modeling. So, for example, the elapsed time for X number of events to occur. And in this plot, what I'm going to do is set the shape to three different values. The first one's going to have a shape value of 1, the second 3, and the third 5. So, first one event, the second one's modeling 3 events, the third one's modeling 5 events. And I'm going to plot all three as we did above using matplotlib on the same figure. And there we go. So we get quite an interesting visualization of what those distributions look like. So you can see from these the probability density functions for these three gamma distributions, and you can see how the appearance of the distribution changes as the value of the shape of alpha, the shape parameter, changes. So you can see that increasing the value of the shape parameter decreases the height of the distribution and widens it. So the distributions also become less positively skewed as the shape parameter increases, as you can see with these. So when the value of the shape parameter is very high, the gamma distribution will start to take on the appearance of a kind of normal Gaussian distribution. You can see that here. So we've got the lowest shape parameter here is 1, which is the blue line, and it kind of just like drops off like a slope essentially, and it's very positively skewed. When we increase the shape to 3, this orange line, it kind of, the peak is much lower, so the probabilities are much lower, but you've got this kind of like still got this positively skewed distribution. When we increase the shape to 5 for the green, it sort of lowers the peak again and makes it more spread out, and it shifts the distribution this way. And you can already see if you kind of kept increasing the shape, you could see how this would keep going and sort of start to look more like a normal or Gaussian distribution. So let's see what that looks like if we kind of plot a gamma distribution using the PDF. Just plot the PDF of a gamma distribution with a very high shape value. So in this case, all I'm going to do is use the stats.gamma.pdf. I'm going to use this array of values between 0 and 300, 1,000 data points between 0 and 300 on the x-axis, and we're going to set our shape to 50, so a very high shape value, and we'll set the loc to 0 and the scale to 3, so a rate of 3 events per unit time. Let's see what that looks like, and you can see there by putting this very high shape value in, the actual shape of the distribution has changed considerably, and it looks very normal and bell-shaped in appearance. And you can see the scale is between 0 and 300 on the x-axis there. Okay, right, so let's have a look now at what happens when we adjust. So we've adjusted the threshold, the loc, we've adjusted the shape. What happens now if we hold those constant and adjust the scale parameter? So to investigate the effects of just adjusting the scale parameter, I'll plot those three gamma distributions again, and I'll set the loc to 0, the shape to 4 for all three of them, but we'll adjust the scale parameter. Okay, so remember the scale captures the rate or mean amount of time between events, and as a rate it's often specified as 1 over lambda. So you can see in the blue, in this plot, but you will see in the plot below, but you can see in the code here, I've kind of set the shape to 4 for all three of them, the starting value, the threshold to 0, but they've got different scales, so 1, 3 and 5 in this case. And we're going to plot all three as we did above using matplotlib on one figure. And now you can see again, similar to adjusting the shape, higher values of the scale parameter reduce the height of the distribution, so it's gone from very peak to a bit flatter to even flatter as we increase the scale parameter. And this would make sense when we consider that the scale captures the mean time between events. So when the time between events is longer, so we've got higher scale values, the probability of higher values for elapsed time increases. Okay, so that's the gamma distribution and kind of how adjusting these three parameters helps. It changes the shape of the distribution, so it's kind of useful to understand how that works, build our intuition about that. But let's talk about some related distributions now. So the exponential distribution is a continuous probability distribution, and we use it to model the time elapsed, the waiting time, until one event occurs. So as such, the exponential distribution is just a special case of the gamma distribution. So a gamma distribution with a shape, an alpha value of 1, is equivalent to an exponential distribution. So the exponential distribution has one less parameter than the gamma distribution, as the shape alpha it's set to 1 by default. You don't get to specify what it is. If you do, then it's a gamma distribution, not an exponential. Okay, so let's play around with this a little bit, but we'll use the SciPy software library to generate data that follows an exponential distribution, and we do this using the expon method here, where what we need to do is specify the scale parameter and the size of the sample of interest. We can also use other methods through SciPy to investigate probabilities for this distribution, because it's a continuous distribution. So we can use the PDF and CDF, and we'll do that. Okay, so this cell here, what I'm doing is simulating, generating data that follows an exponential distribution using the SciPy expon method and the random variates method. So you've seen me do this before in previous videos. I'm using stats.expon.randomvariates RVS, and we're specifying the scale, the rate, 40 events, and the size of our sample, 10,000. And I'm saving this as a new object called expon_var, exponential variable, something like that. And we can create a histogram. Although it is a continuous distribution, we can create a histogram. Matplotlib will do the work for us and figuring out the bin size to visualize what the distribution of our data looks like. So let's do that now. All I'm doing here is I'm basically doing plt.hist. I'm telling it we want to see the density, so the probabilities on the y-axis, and we're using this expon_var object we created. So let's look at that. There we go, and that's what it looks like essentially, which is kind of similar to our gamma distribution when we specified lower shape values, a shape value of 1, for instance. So although it's a continuous distribution, like I said, we can obtain a histogram. Gives us the densities based on the rate roughly. We can likewise obtain the probability density function for our data. So let's do that here. I'm basically creating a new object called X. It's a NumPy array of 10,000 values between 0 and 400. I'm going to pass that in as the data we're going to use. We're setting loc equals 0 and scale equals 40. So let's have a look at that. And notice I've used the expon.pdf methods. So what we can see here is this with the exponential function. You see this kind of shape. It tapers off very quickly and is very positively skewed. Okay, so we can also use the PDF method to obtain. So we've just plotted the PDF there, but we could use the PDF method and specify, rather than passing a vector of values to it, we could just specify a single value and return a probability for us. So we can obtain the probability for a given value on the x-axis. So for example, if we want the probability of waiting 5 time units before an event occurs with a rate of occurrence, a scale of 40, essentially. So if we use stats.expon.pdf, say we're waiting the probability of waiting 5 time units with a locus 0 and a scale of 40. And if I run this, we get, if we round it to 2 decimal places, we get a probability of 0.02. So about a 2% probability that we would see an event in exactly 5 minutes with a rate of occurrence. If we would see one event, that is, in exactly 5 minutes with a rate of occurrence of 40. I'm assuming we would likely see more because the rate of occurrence is 40 per time unit normally. It's quite rare to see that, I imagine, just seeing one. Okay, so similarly, we can use the CDF method to obtain probabilities that we would have to wait a given time or less before observing an event when the rate is 40. Okay, in this case, the probability we would see an event occur in 50 minutes or less, for example, when the rate is 40, we can use the stats.export.cdf, so the cumulative density. And what we see is we've got a probability of 0.71349, etc. So we can see when the scale, so the mean time between events is 40, there's a 71% probability we would observe an event within 50 minutes or less. Okay, right. So that's the exponential. What about the Erlang distribution? As I said, that's also a special case. The Erlang distribution is a special case of the gamma. So recall that the shape alpha of the gamma distribution models the number of events you're modeling. So it's the number of events you're modeling. It could be 1, 2, 3, etc. It could be any value because it's a continuous distribution. So it could be a decimal value. So for example, the elapsed time until 3 accidents have occurred, something like that. Whereas the exponential distribution is the gamma distribution with a shape value alpha of 1, the Erlang distribution is equivalent to the gamma distribution when the shape value is set to an integer, so any integer. So the shape parameter for a gamma distribution must be a positive value, but need not be an integer. So like I said, you could put floating point decimal numbers in. But when it is an integer, then the gamma and the Erlang are identical, essentially. So as with other distributions, we can simulate data that follows an Erlang distribution using the Erlang method in SciPy. There's so much stuff in these software libraries, it's absolutely brilliant. And we can also invoke the random variates RVS method. And then we can also use this PDF and the CDF to investigate specific probabilities. So let's simulate some data that follows an Erlang distribution, and we're going to specify shape of alpha equals 3. So it has to be an integer value because it's the Erlang distribution. If you enter a non-integer value here, it won't be enforced, but you'll get some sort of warning message. It won't like it, basically. So I'm creating a new object called Erlang variable Erlang_var, and we're using stats, SciPy stats.erlang.random variables. I'm specifying our shape is 3, so it is an integer, where the locate threshold is 0 and our scale is 1, and we're simulating kind of 10,000 data points here. Okay, let's create a histogram of this object as we did above, and ask for densities. So it's going to give us densities on the y-axis, probabilities essentially, and that's what it looks like. And you can see that's kind of, if we plot the PDF as well with the same parameters, you can see that's kind of similar sort of shape there. The histogram is obviously, it's discretized the values and chosen some sort of bin size for us. Really, it's the PDF that we're more interested in. But if we look at this here, you can see this is kind of you're going to get the same shape with a gamma distribution when you have a shape value of 3, essentially. Okay, so as we did above with the exponential, we can also use the PDF method to obtain specific probabilities. We passed the vector in above that we created here. We passed data np.linspace 10,000. We passed that in for the plot. But if we use the PDF, stats.erlang.pdf method, and just pass a specific value, and then the parameters for our distribution. So for example, the probability of waiting exactly 5 time units, for example, minutes before our alpha equals 3, so our 3 events occur, with a rate of occurrence, a scale, of 1 event per unit time. So there's an 8% probability that in 5 minutes, in 5 time units, we'd see our 3 events occur when the rate is 1 event per unit time. So we'd probably have to wait longer if to see those events, I guess. Okay, so the last one here we'll kind of just demonstrate is the cumulative density function, CDF. We can use that method to obtain probabilities that we'd have to wait a given time or less before observing, say, 3 events. The 3 events specified by our shape when the rate is 1 per time unit. So in this case, the probability we would see 3 events occur in 6 time units or less is what I'm going to pass as the argument here. So I'm using stats.erlang.cdf this time, saying 6 time units with an alpha of 3, locus of 0, and a scale of 1. And what we should see is we've got about a 94% cumulative probability that we will see our modelled number of events, 3 or fewer, in 6 time units. Okay, right, so that's it. That's all I'm going to do on the gamma, exponential, and Erlang. So what I've done, just a quick recap, discussed the properties of the gamma distribution and how changing the parameters influences the appearance of the distribution. I've also described the exponential and Erlang distributions as special cases of a gamma distribution. So if you change the loc, or the threshold of a gamma distribution, it shifts the starting value to the left or right on the x-axis. If you increase the shape parameter, for example, this causes elapsed time to increase and makes the distribution wider and flatter. This is because we're modelling more events and it will take longer before those events are observed when they occur at a fixed rate. Increasing the scale parameter, or what's known as the rate, also increases the width of the distribution and reduces the height as the mean time between events is increasing. Okay, and the exponential distribution is the gamma distribution with a shape value set to a default of 1, for example, elapsed time for 1 event to occur. The Erlang distribution is the gamma distribution when the shape value is set to an integer value. Okay, and they're going to be positive values, essentially. Right, okay, so that's that. I think in the next video what I'm going to do is talk about the geometric distribution. Couple left, and then I'll be finished with describing probability distributions for a while. Okay, I hope this was interesting and helpful. Thank you for watching.